All right, folks, good morning. Today is Tuesday, 10/6. Your homework is to watch the video I'm creating right now and read lesson 35 and then do lesson 35, numbers 1 through 25, just like it was a normal day. So let us get started. All right, so today we are going to be looking at lesson 35, which is on integration rules. These are really integration shortcuts, but you're never going to learn, not now, you're not going to learn the long way to do integration, not this year. But just like for differentiation, we had the limit definition of the derivative and then we got shortcut rules. Okay? For integration, there's a long way to do it, which you're not learning, and then there's just the shortcut rules. That's what we're doing today, integration shortcut rules. Okay. So let's review first. Let's review some of the differentiation shortcut rules. All right, let's just a few of them. If I say d dx x to the n, what would you write? You'd write nx to the n minus 1, right? If I said d dx, differentiate with respect to x, c, which is some constant, times a function f of x, how could you rewrite that? Yeah, you can pull the constant out. You can always pull a constant out of a derivative. Never a variable, but you can always pull out a constant. So you get this, the constant times d dx of f of x. All right, let's try some other derivative rules, see if you remember them. D dx of e to the x. That's just e to the x. How about d dx of natural log of the absolute value of x? All right. Do you remember what that's 1 over x? Just got to memorize these rules, folks. D dx of sine of x, remember what that is? Cosine of x. If I said, what is d dx of cosine of x, what would you tell me? Negative sine of x. All right, and if I said d dx of, f of x times g of x, this function right in here, which is f times g, it's a product. So you must use what rule? The product rule, which is the first times the derivative of the second plus the second times the what? Derivative of the first. All right, so you know all these shortcut rules for differentiation. We have to learn some shortcut rules now for integration, and you have to keep them as opposites in your mind and not blend them together. I'm telling you, the biggest risk is that they blend together and you integrate when you should have differentiated and vice versa. And this happens to people all the time, so you definitely want to pay attention. So these are integration shortcut rules. Again, if you're asking, well, what was the long way for integration? You never learned it. For differentiation, the long way is the limit definition of the derivative, and then you had your differentiation shortcut rules. For integration, there's a long way to do it, which you don't know, not yet at least. And then there's these shortcut rules, which you're memorizing right up front, okay? So here's the first rule. It's going to be if I take the integral of a constant, such as some constant, k, I'm going to call it k instead of c. I could call it whatever I want. It's a constant. The integral is going to be kx plus c. Kx plus c. It makes sense. In your brain, if you reverse this, right, so you took like d dx of kx plus c. Let's see what you'd get. Well, the derivative of kx is just going to be k, and the derivative of c is just going to be 0, so this is k. So that works. All right. So you need to memorize this rule. Put it in your list of integration rules. In the back of your book, you're going to need a list of differentiation rules. You're going to need a list of integration rules. You have a lot more differentiation rules coming, a lot more integration rules coming. So you just want to make a complete list. If you've run out of space, rewrite it. It can't hurt to practice. Okay, so this is a rule you're going to need for integration shortcuts. I'm going to go ahead and give you another rule for integration shortcuts shortly. Let's just go ahead and practice with this one, okay? Here is an example. What if I said, what's the integral of 5 dx? 5 dx. Well, you think this rule is pretty clear, 5x plus c. And we can check that. If we d dx 5x plus c, we just get 5, which is exactly what we have as our integrand. What we're integrating is called the integrand. It's the function that we're integrating. Okay. All right, let's try another simple example. Actually, you know what? I think we can go ahead and give you another shortcut rule is what we can do. So let's do that. Here's a shortcut rule. Integral of k, some constant, times a function of x dx. This might be x squared dx, natural log of x dx, e to the x dx, whatever function it is of x. If you also have a constant in front of it, just like when you differentiated, you could pull the constant out. And so you get k, which we're calling the constant in this side. We do that in integration. We often call the constant k because we get this other constant generated for integration called c, so as not to confuse them. That's the only reason. Right? So this is k times the integral of f of x dx. Right. Or if I wanted to write that differently, I could write it as k big F of, well, let's not go there. Let's not go there. Okay? Probably best not to go there. K integral of f of x dx. Pull out the constant. That's the rule here. So this is the second shortcut rule for integration you got. All right? So let's practice. If I have something like 8x dx, all right, well, I could pull out the 8 if I want to. For sure, I could do that and then integrate. Or I could pull out part of the 8. I'm going to choose to pull out part of the 8. Watch. And I'll show you why in a second. 4 times 2 is 8, right? So I'm just going to pull out part of the constant. I can do that. I pull out 4, leaving me 2x. Now all I have to do is think, hey, what's the antiderivative of 2x? And you know the answer to that. The antiderivative of 2x is x squared plus c. Am I right? And then you still have this 4 outside the integral. Take derivative of x squared, it's what? 2x. Okay. Now, something you just need to realize is this c out here is a constant, so I'll call it c sub 1 for now. When I actually multiply through, this is how you always multiply through, 4x squared plus c. Because this would be 4c sub 1, but this is now just c sub 2. And since it's just an unknown constant, you don't bundle up all this extra information. So you don't have to write 4c sub 1 or 4c. You just write c. One way to handle this is to do the integration all first and then just add a plus c to the end. But this is mechanically what's going on, okay? So we won't write c sub 1 here, we won't write c sub 2 here. We'll just, instead of writing 4c, we'll just write c. Realizing it, 4c and c are both constants, okay? Good, that was an example. I think we try another example. Okay, what if I said, what is 4 times cosine of t dt? So my integrand is 4 cosine t. Well, I know by this rule I can pull out the constant 4. So I'm going to pull the whole thing out, leaving me with cosine of t dt. Okay, I'm going to integrate with respect to t. So t is going to be my independent variable. And I just got to think, what do I differentiate to get to cosine of t? The answer is, oh yeah, sine of t. Derivative sine of t is cosine of t. So this is just 4 times sine of t plus c. Now again, this is like c sub 1. So if I multiply, I get 4 sine of t plus some c sub 2. I don't have to call it 4c. or for c sub 1. I just rename it c sub 2. But no one ever actually puts the subscripts down, so you just call it plus c. Okay? What if I said this example? What is the integral of sine of u du? Integrand is sine of u. I'm going to anti-differentiate with respect to u. My independent variable is going to be u. Well, there's an implied constant of 1 here, which is also the implied constant -1 times -1. -1 times -1 is 1. So what I could do is pull out a -1 in front. It's a constant. Pull out -1 in front of the integrand. Leave a -1 inside the integrand like this. And you're like, why'd you do that? Well, as long as you understand -1 times -1 is 1, so that's the same thing. Then if I said, what's the antiderivative of negative sine of u, what would you say? Well, there's a negative sign out there, right? So I'm leaving that. The antiderivative of negative sine of u is cosine of u, isn't it? What's the derivative of cosine of u? Negative sine of u. Okay, plus c. So when I write this, finally, I'm going to write it as negative cosine of u plus c, not minus c, because, again, this is negative c sub 1. But negative c sub 1 is just, we just call it c sub 2. And then we never actually write c sub 1 or c sub 2. All right. Next, we have one more rule that we want to definitely talk about explicitly today. So that's going to be this rule, and you'll use it all the time. So if I have an integral of x to the n dx, so my integrand is a what type of function? It's a power function, right? Like x squared or x cubed or whatever. The integration will be x to the n plus 1. Remember when we differentiated, it was n minus 1, now it's n plus 1, over n plus 1. Okay, over n plus 1. Because before we would bring whatever was in the numerator over in front and then subtract 1. Now we bring whatever's in the numerator, add 1, and divide by that new number. Okay. Yeah, let's see. Let me show you that in reverse. Maybe that'll help. d dx, if I differentiated this thing, x to the n plus 1 over n plus 1. Remember, that's just a constant at the bottom. Okay. This is going to be, what's the derivative of x to the n plus 1? You bring n plus 1 out to the front, x to the n plus 1 minus 1, which is just n, over this constant, because constants don't affect derivatives, you can pull them in or out. N plus 1 is just a constant, n plus 1, so this cancels out, and you just get x to the n. This clearly is the integration rule, because the differentiation gets you back to your integrand. Do you see that? Okay, so here's a rule you just need to memorize. Of course, you need to have plus c, right? You always have plus c on all these functions. Okay, so let's do an example. Our example is going to be 4x cubed dx. All right, well, if I want to do this purely now using this formula right here, let's do it two ways. First, let me do it how I would do it, which is to say, oh, this is just x to the 4th plus c. Because if I think it backwards, what is d dx of x to the 4th plus c? Well, d dx of x to the 4th is 4x to the 3rd, and then d dx of c is 0. So that clearly is the answer. But if I wanted to use this system, how would I do that? Let's try it again using the system. Well, the system tells me I just want a power function, not a constant. So I'll bring the constant out, leaving me with x cubed dx. And now I'm going to integrate using the system. So I got 4 times. What's the integral of x cubed? Well, it looks like I got to add 1 to the top. So that gets me x to the 4th over, well, if it was x to the 4th, and this is 4, right? Because it's the same number there. Plus c, which is going to equal x to the 4th plus c, which is the same answer we got if we just noticed it could be worked faster. Example. Let's do the integral of 5 times s to the negative 20th ds. I'm integrating with respect to s. My integrand is an s. It makes sense. So I could pull out the 5 because it's just a constant. Leave me with x to the negative 20 ds. I've got a power function, so I just follow the rule. 5 times, let's integrate s to the negative 20. What do? I add 1. So that's x to the negative 19 over negative 19. Okay, plus c. Now in theory, right, once again, in theory, if you're still following the theory here, this is really like this. But when we multiply the 5 times c1, we'll just get c sub 2. So it really doesn't matter that I'm sticking the c outside here right now. I'm just jumping ahead of the game, which is eventually what your brain will do. Okay? So this is going to equal just 5x to the negative 19 over, sorry, it's going to equal negative 5x to the negative 19 over 19. I just brought that negative sign up there. And plus c. That's my answer. Let's try maybe a couple more examples of this one because the power rule is going to show up all the time, just like it did for differentiation. Can't avoid it. So let's say we had 1/3 cube root of t squared dt. Well, the first thing you need to realize, this is cube root and this is t squared, so they don't cancel. It's not like square root and square. And you can rewrite this. The 1/3 is a constant, so I can bring it out. The cube root of anything is just that thing raised to the 1/3 power. So 1/3 power times 2 is the 2/3 power. So this is t to the 2/3 dt. T to the 2/3 dt. Well, no problem. I'm anti-differentiating with respect to t, so I'm going to get the 1/3 on the outside times the antiderivative here. Well, what's the rule? The rule is you add 1. So 1 is the same as 3/3. That's going to be 5/3. So I'm going to get t to the 5/3 over 5/3. That's the rule. And theoretically, again, it'd be plus c over here. When you multiply times 1/3 times c, though, don't say 1/3 c, just say c, because it's really c sub 2. Okay? So what is this going to come out to? It's going to come out to 1/5 t to the 5/3 plus c. Okay, let's just double check that. We'll ddt 1/5 t to the 5/3 plus c. We'll see what we get. Well, if you differentiate by the 5/3 in the front, leaving you with 1/3 t, subtract 1, which is 3/3, and you're leaving with 2/3. Derivative of c is just 0. So there you go. And is that my integrand? Well, let me see. Let me rewrite it. It's t to the 2/3. It's like t squared to the 3rd root. That's what we started with. So we're good. This is working out for us. All right. Shall we try a couple more? Let's try a couple more just because, yes, this rule will show up all the time. So if it's written like this, does this get more confusing to you? It shouldn't be. It's the same stuff we've seen, but again, appearances can confuse. Do you see a constant? You see 3, pull that out, leaving with du over the square root of u. Is that confusing? It shouldn't be. How can I rewrite 1 over the square root of u? That's right. You can write it as u to the negative 1/2 power. Don't forget your du. Okay. So we're going to integrate with respect to u. And so how do we follow this rule? You add 1 to the power, so you're going to get u to the 1/2 over 1/2 plus what? C. And there's a constant of 3 out here. Now again, theoretically you'd be doing this, okay? But that's just 6u to the 1/2 plus c, because 3c sub 1 is just c sub 2, and we don't even bother label it, okay? So if you want to do all the integration first and then just tack on a plus c, you could do that. And that might go better for you, I don't know. Last example is going to be the integral of 5z to the pi dz. The integral of 5z to the pi dz. Well, we know we could pull out the 5, and we've just got z to the pi dz. What type of function is this? Is this exponential? Is this power function? It's just a power function. It's no different than like x squared. Instead of x, we're calling it z, and instead of squared, we got pi. Pi is about 3.14. Okay, so just look at it like a power function, power rule, anti-differentiate with respect to z. So you're going to get 5 times. This time, let's just integrate what's in here. Okay, so what do? You add 1. So z to the pi plus 1 over pi plus 1. And then slap on a plus c. At this point, I think we just see it's going to yield plus c at the end. We don't have to go through all this mechanics. All right, so that's my answer. I mean, I could write it as 5z to the pi plus 1 over pi plus 1 plus c if I wanted to, but it's the same thing, right? Okay, so you have integration rules and anti-differentiation rules, right? Let's say I said, what is the integral of cosine of x dx? What would you say? You should be saying sine of x plus c. So you're going to want to write these on your integration pages. Just reversing these processes in your brain, right? If I said, what's the integral of negative sine of x dx, what would you say? Well, you'd say cosine of x plus c, wouldn't you? So you want to put these on your integration shortcut rules page. If I said, what is the integral of 1 over x dx, which of course could be written, folks, as the integral of dx over x, which might look more confusing, but that's the same as 1 over x dx. What's the antiderivative of that going to be? Well, you know, it's the natural log of the absolute value of x plus c. The derivative of natural log of x is 1 over x. The derivative of natural log of negative x is 1 over x. The natural log of the absolute value of x is 1 over x. This is the most complete form of the antiderivatives. You have to use the absolute value form here, okay? Or if I said, hey, what's the antiderivative of e to the x dx, antidifferentiate with respect to x, and you get e to the x plus c. Remember, plus c whenever you're integrating. All right, so these rules should also go on your list. Just think about it in reverse. Derivative of e to the x is e to the x. Derivative of natural log of absolute value of x is 1 over x. Derivative of cosine of x is negative sine of x. Derivative of sine of x is cosine of x. Yes, these are all correct. All right, folks, you want to do lesson number 30. What is this? 35. We just did lesson number 35, and so that's what you want to do for homework. Yep, lesson 35. Okay? I think tomorrow I'll probably give you a worksheet again, but today I want you to do this lesson. It's a pretty simple lesson. It's just putting your mind in reverse, basically. Thank you.